Hey, what's up you guys? This is Ilarion Garbuzov with you, and today we'll have a talk on convolutional neural networks. Let's talk about it! Guys, I need your feedback, so push the like button, crash the like button, and subscribe to my video channel on data science.
In deep learning, a convolutional neural network is a class of deep neural networks, most commonly applied to analyzing visual imagery. They have applications in image and video recognition, recommender systems, image classification, medical image analysis, natural language processing, and financial time series. Convolutional networks were inspired by biological processes in that the connectivity pattern between neurons resembled the organization of the animal visual cortex. Individual cortical neurons respond to stimuli only in a restricted region of the visual field known as the receptive field. You can see it on the slides. The receptive fields of different neurons partially overlap such that they cover the entire visual field. The name convolutional neural network indicates that the network employs a mathematical operation called convolution. Convolution is a specialized kind of linear operation. Convolutional networks are simply neural networks that use convolution in place of general matrix multiplication in at least one of their layers. Architecture of convolutional neural networks. A convolutional neural network consists of an input and output layer as well as multiple hidden layers. The hidden layers of a CNN typically consist of a series of convolutional layers that convolve with the multiplication or other dot product. The activation function is commonly a RELU layer and is subsequently followed by additional convolutions such as pooling layers, fully connected layers, and normalization layers, referred to as hidden layers because their inputs and outputs are masked by the activation function and final convolution. On the slides you can see the typical architecture of the convolutional neural network and the model that we will build in the second part, where I'll show you the code. Building blocks. A CNN architecture is formed by a stack of distinct layers that transform the input volume into an output volume through a differentiable function. A few distinct types of layers are commonly used. Convolutional layer. The convolution layer is the core building block of a CNN. The layer's parameters consist of a set of learnable filters or kernels, which have a small receptive field but extend through the full depth of the input volume. During the forward pass, each filter is convolved across the width and height of the input volume, computing the dot product between the entries of the filter and the input and producing a two-dimensional activation map of that filter. As a result, the network learns filters that activate when it detects some specific type of feature at some special position in the input. Stacking the activation maps for all filters along the depth dimension forms the full output volume of the convolutional layer. Every entry in the output volume can thus also be interpreted as an output of a neuron that looks at a small region in the input and shares parameters with neurons in the same activation map. Three hyperparameters control the size of the output volume of the convolution layer: the depth, stride, and zero padding. The depth of the output volume controls the number of neurons in a layer that connect to the same region of the input volume. These neurons learn to activate for different features in the input. For example, if the first convolutional layer takes the raw image as the input, then different neurons along the depth dimension may activate in the presence of various oriented edges or blobs of color. Stride controls how depth columns around the special dimensions, width and height, are allocated. When the stride is 1, then we move filters 1 pixel at a time. This leads to heavily overlapping receptive fields between the columns and also to large output volumes. When the stride is 2, then the filters jump 2 pixels at a time as they slide around. Similarly, for any integer s, a stride of s causes the filter to be translated by s units at a time per output. Sometimes it is convenient to pad the output with zeros on the border of the input volume. The size of this padding is the third hyperparameter. Padding provides control of the output volume spatial size. In particular, sometimes it's desirable to exactly preserve the spatial size of the input volume. pooling layer. Another important concept of CNNs is pooling, which is a form of nonlinear downsampling. There are several nonlinear functions to implement pooling, among which max pooling, you see it on the slide, is the most common. It partitions the input image into a set of non-overlapping rectangles, and for each such subregion, outputs the maximum. Intuitively, the exact location of a feature is less important than its raw location relative to other features. This is the idea behind the use of pooling in convolutional neural networks. The pooling layer serves to progressively reduce the spatial size of the representation, to reduce the number of parameters, memory footprint, and amount of computation in the network, and hence to also control overfitting. It is common to periodically insert a pooling layer between successive convolutional layers in CNN architecture. The most common form is a pooling layer with filters of size 2x2 applied with a stride of 2, downsamples at every depth slice in the input by 2 along both width and height, discarding 75% of the activations. The RELU layer is the abbreviation of Rectified Linear Unit, which applies the non-saturating activation function. It effectively removes negative values from an activation map by setting them to 0. It increases the non-linear properties of the decision function and of the overall network without affecting the receptive fields of the convolutional layer. RELU is often preferred to other functions because it trains the neural network several times faster without a significant penalty to generalization accuracy. Fully connected layer. Finally, after several convolution and max pooling layers, the high-level reasoning in the neural network is done via fully connected layers. Neurons in a fully connected layer have connections to all activations in the previous layer, as seen in regular non-convolutional artificial neural networks. Their activations can thus be computed as an affine transformation with matrix multiplication followed by a bias offset, vector addition of a learned or fixed bias term. The loss layer specifies how training penalties the deviation between the predicted output and true labels, and is normally the final layer of a neural network. Various loss functions appropriate for different tasks may be used. Max loss is used for predicting a single class of k mutually exclusive classes. Sigmoid cross-entropy loss is used for predicting k independent probability values. Choosing hyperparameters, and on that we'll choose between number of filters, filter shape, and max pooling shape. CNNs use more hyperparameters than a standard multi-layer perceptron, while the usual rules for learning rates and regularization constants will still apply. The following should be kept in mind when optimizing. Number of filters. Since feature map size decreases with depth, layers near the input layer will tend to have fewer filters, while higher layers can have more. To equalize computation at each layer, the product of feature values with pixel position is kept roughly constant across layers. Preserving more information about the input would require keeping the total number of activations non-decreasing from one layer to the next. The filter shape. Common filter shapes found in the literature vary greatly and are usually chosen based on the dataset. The challenge is to find the right level of granularity so as to create abstractions at the proper scale, given a particular dataset and without overfitting. Typical values are 2x max pooling shape. Typical values are 2x2. Very large input volumes may warrant 4x4 pooling in the lower layers. However, choosing larger shapes will dramatically reduce the dimension of the signal and may result in excess information loss. Often, non-overlapping pooling windows perform best. Regularization methods in CNN. Regularization is a process of introducing additional information to solve an ill-posed problem or to prevent overfitting. CNNs use various types of regularization: the dropout, artificial data, early stopping, a number of parameters, and weight decay. Dropout. Because a fully connected layer occupies most of the parameters, it is prone to overfitting. One method to reduce overfitting is dropout. At each training stage, individual nodes are either dropped out of the net with a probability 1 minus p or kept with a probability p, so that a reduced network is left. Incoming and outgoing edges to a dropped out node are also removed. Only the reduced network is trained on the data in that stage. The removed nodes are then reinserted into the network with their original weights. Artificial data. Since the degree of model overfitting is determined by both its power and the amount of training it receives, providing a convolutional network with more training examples can reduce overfitting. One of the simplest methods to prevent overfitting of a network is to simply stop the training before overfitting has had a chance to occur. It comes with the disadvantage that the learning process is halted, and it is called early stopping. Number of parameters. Another simple way to prevent overfitting is to limit the number of parameters, typically by limiting the number of hidden units in each layer or limiting network depth. Weight decay. A simple form of added regularizer is weight decay, which simply adds an additional error proportional to the sum of weights L1 norm or squared magnitude L2 norm of the weight vector to the error at each node. When we construct the CNN model, we need and fit it on the train and test data. We need to fine-tune it. For many applications, the training data is less available. Convolutional neural networks usually require a large amount of training data in order to avoid overfitting. A common technique is to train the network on a larger dataset from a related domain. Once the network parameters have converged, an additional training step is performed using the in-domain data to fine-tune the network weights. This allows convolutional networks to be successfully applied to problems with small training sets. And as soon as we've got our 15 minutes, then let's see how it works in Python. We would use Google Colab, and we would start with loading the libraries. We would import TensorFlow as TF. TensorFlow is an open source platform for creating algorithms in machine learning, especially neural networks. We would import NumPy as NP. It's a library which includes concepts from linear algebra, such as arrays and matrices. And from TensorFlow, we would import Keras. It's an API provided by TensorFlow and is one of the leading high-level neural networks APIs. As soon as we import libraries, we need to acquire the data. We would use Fashion MNIST, a dataset. It's a dataset containing more than 60,000 different images of fashion. After that, we need to split our data into training and test data, and you see it over here. We would import Matplotlib to plot our data into images that are visually appealing. And you can, by image show, using Matplotlib, we can see that there are 28 by 28 pixels, and depending on the item, every pixel has its own value from 0 to 255. And you can see it on the screen. That's the list with our image. And here is the image that you can see in MNIST dataset. After that, we need to normalize the data dimensions so that they are of approximately the same scale. We divide training and test images by 255. And we need to reshape input data from 28 by 28 to 28 by 28 by 1, because we need to use it in convolutions. Here we're reshaping the data. And after that, our data is ready to feed the model, but first of all, we need to create our model. We would use Keras sequential model. It defines a sequence of layers in the neural network, and we must define the first input shape in the first layer of the neural network. So in the first neural network, the input shape would be, as soon as we reshaped it, 28 by 28 by 1. And we would use convolutional 2D layer with 64 filters and the kernel size 2, the same padding and the activation RELU as and you know all of this from our first part, theoretical part of our lesson. After using the convolution 2D layer, we would use max pooling with the pool size 2x2. And after that, we would use dropout with parameter 0.3. And this would be our first part of the full layer. This we would use the same in the second part, convolution 2D, max pooling, dropout. After that, we need to convert our 2D array of pixels into 1D of each pixel, and we would use flatten, a fully connected layer, and a dense layer with 256 neurons and the RELU activation function. After that, we'll use dropout with parameter 0.5. And at the end, would use the dense layer with 10 neurons and the activation function softmax. This would takes a set of values and effectively pick the biggest one. And we are using 10 neurons because we have 10 different classes in our data set. And the softmax would show the probability that our example is in this proper class. Let's take a look at the model summary. Here is the model summary. You see all the layers that we add to our model, and the total parameters in this shallow, pretty shallow model is 400,000. And all the parameters are trainable. After that, we need to compile our model, and we would compile it with Adam optimizer. We would choose the sparse categorical cross entropy loss, and our matrix would be accuracy. After compiling the model, we can fit it with our training examples and would fit it on our training examples and training labels on 5 epochs. So we are fitting our model. After fitting our model, we can see the history, and we see that the accuracy is increasing while the loss is decreasing. So the model is not overfitting on our training set, and we can evaluate our model on the test data set, and we see that we've got pretty good accuracy. So our accuracy is 90%, and the loss is 0.26. So that's how the model looks like, the convolutional neural network. And here how in the first part you saw how it looks like in theory, and here you can see how it looks like in Python using TensorFlow and Keras API.
Thank you. See you tomorrow.